Hello, class. We are recording. I would say that this is probably the latest lecture that I've done, but it's to really finish up our analysis, at least of the metallic conductor communication channel, type of communication transmission. And this last one that I want to do, now I've looked at, I haven't done one specifically for power transmission. I think that you can figure that out from the two-wire system that I did, which is exactly the same type of transmission system that you have for high voltage transmission, power. The last one that I want to look at is one that's going on inside your phone, and one that's going on, not much tea left, and one that's going on inside computers, and a lot of things. And in fact, I wrote down a couple things before I started this lecture because it's on microstrip transmission lines. But what I wanted to write down is this. There's two equations here, really. This is one equation for the characteristic impedance of a microstrip transmission line. Now, I also want you to realize that this microstrip transmission line here, this may be a conductor, and this may be a conductor, right? The whole bottom of this is a conductor, right? So we've wave soldered the entire bottom of this PC board with copper, whatever you want to think about it. And then we've also got a line up here too that also is made out of copper, and it's a certain width. And in fact, the width that we've got and the height play a big part in what the characteristic impedance of this communication line is going to be. Now, you probably see that I've got 16 volts on the top and I've got 0 volts on the bottom. It doesn't really matter what the voltage differential is. I just wanted to show you that there was an electric field across. Now, this part in the middle here of the printed circuit board is made out of epoxy, right? And you're probably thinking, well, let's see, epoxy, the relative permittivity of epoxy is about 4.5. That's right. It is 4.5. And I'm amazed you knew that. But I'm getting down to less pens. Anyway, the red pen seems to be working pretty good. So yes, the epoxy inside has a relative permittivity of 4.5. Now, I wanted to write down a couple things here because I wanted to point out, because you're going out and you're going to become engineers, and that's not always exactly the same as the theory that you learn in your classes, right? So the truth is, I'm going to use this expression here, and in fact, what I'm really using there, let me just write this down, is, I'll write it over here. So Z sub 0 is actually eta divided by W over H plus 2. So this is basically exactly this equation right here, and I will work through that in just a minute. Before I do that, I want to talk a little bit about the geometry of this communications waveform. So if you look at the the way that we've got it right here. You can see that I've got an electric field, and the electric field is going in this direction, right? So I'm just going to draw my electric field lines here. And so that's my electric field lines, and that also sort of breaks it up, because that shows that, you know, that's flowing in that direction. Now I'm going to break this up into cells, right? And I think everybody can see that I've got 1, 2, 3 cells in series. And so these 3 cells in series right here, this distance right here, I'm really going to call n sub s. And then when we look at these cells that are in parallel, let's call that n sub p, because those cells are all in parallel, right? Does everyone see that? And so when we look at the communication circuit, you see that we've got resistance and inductance in series. We've got capacitance in parallel, and of course we have conductance G prime, which we always say is 0. This is L prime, that would be C prime, and of course this is R prime. So when we look at the communications circuit, and we see that we've got, you know, a certain amount of cells that are in parallel and a certain amount of cells that are in series, we can say that L prime, which is in series, right, in the communication circuit, right? I'm just going to block that off for a second. So L prime is going to be n sub s over n sub p times mu. And of course that mu would be the mu of the dielectric, right? So everyone realizes that. And by mu, I mean mu sub 0 times mu sub r. Now, that would be our thing. And when we look at it, we can see that, you know, n sub s is really h, isn't it? Isn't n sub s really h, and n sub p is really w, the width. Don't get w's confused with omega, by the way. This would be w. The t here, I'm just going to point that out. T equals thickness. And let's just look at this equation again. You can see that that's a much more a detailed equation, an empirical equation that we've really gotten from a lot of experimentation on microstrip transmission lines. And when you go out and you start working as an engineer, are you going to be working with this theoretical equation, or are you going to be working with this equation when you start to figure out what the ratio of width to height of this microstrip transmission line is when you want impedance matching between this, right? So you want the impedance of this, which is, let's say, 50 ohm, to match up with the next thing you're connecting it to, which also has to be 50 ohm. Are you going to be using this equation, or are you going to be using this equation? So the truth is, when you go out and you actually start working like an engineer, yes, you're going to be using this equation. And you can see that there's another variable in that equation too, right? Not only epsilon sub r, but that's going to be dictated by the epoxy that you're using as the dielectric here for the communication channel. But, you know, T is also another variable that you don't have in this equation. You only have W and H. And I'll explain the two in just a second. So anyway, this is what we get. We get n sub s and n sub p. So what the equation ends up working out to is mu of the dielectric, right, over W over H plus 2. All right. Now, why is it plus 2? I'm just going to put a parentheses around here. Why is it plus 2? Right? You said that W was n sub p, and you can see here that really we could rewrite this as mu over n sub p over n sub s, right? I think everybody can see that. I'll just write it out here. So this would really be mu over n sub p divided by n sub s. And if you remember, we said that n sub p, well, that's really like W, and n sub s is really like H. Well, where does the 2 come from? Well, let's expand that out a little bit. So really, if we made a common denominator here and put H in the bottom and H in the top, that really, W over H plus 2 equals W plus 2H over H. Does everyone see that? Right? Okay. Okay, so really what we're saying is we've got W plus. Now what is that plus? Plus 2. W plus 2H. Well, look at H here. See how far H is? About that far. So let's go out 2H, about out here. So what it's saying is that we're still getting fringe effects out here, right? We're getting fringe effects, and we have to take into account those fringe effects in addition, and that's where the 2 comes in, 2H, right? W plus 2H. So we're going out W plus 2H here, and that's what we end up getting. That's where that 2 comes from. Now I'm going to do the same thing when I look at capacitance per unit length. So when we look at capacitance per unit length, you can see that that's in parallel. So instead of it being n sub s over n sub p, it's n sub p over n sub s, right? Times my permittivity of the dielectric. And of course, the permittivity of the dielectric. Now, we should say that everything that we ever look at here, mu sub r equals 1. The only thing that where it wouldn't equal 1 is if we were talking about steel or, steel. Basically steel, iron, something like that, it wouldn't be equal to 1. But most of the time, it's just equal to 1. That's not so with epsilon, though, is it? Because epsilon r, we know, is going to be 4.5 when we do an example here. And not only that, if we do switch this around, wouldn't this be epsilon divided by n sub s over n sub p? So I've got epsilon divided by n sub s over n sub p, right? Just like that. So n sub s, if we look at that as height, and that is, so it would be better just to keep it like this, because n sub p, just like we have here, is w, n sub p is w there. So the way that I'm going to write this is I'm going to say that this is W over H plus 2, and again, that 2 is due to fringing effects, times epsilon sub 0, epsilon sub r. Does everyone see how I got that? I hope. Okay, good. Now, the next step that I'm going to make here is looking at what the characteristic impedances, and I'm going to use a lossless approximation here. So I'm going to write that lossless approximation. And why am I making a lossless approximation? And what type of lossless approximation am I making? Well, if you remember, I said that Z0 is equal to the square root of R plus J omega L. I derived this in an earlier lecture, divided by G plus J omega C. Right? So if R is equal to 0 and G is equal to 0, don't we just get the square root of J omega L over J omega C? I think everybody can see what's going to happen here. That just gives me the square root of L prime over C prime. You know, if we do L prime over C prime, the square root of L prime over C prime, let me just make a little bracket here, and let's just do that. Well, L prime is going to be mu divided by W over H plus 2, right? And then if we divide that by epsilon times W over H plus 2, I think everybody can see, now I've got to take that to the square root, of course, but everybody can see that we're going to lose the W, yeah, because this is, hey, wait a second, what I got here? L divided by Z. What, have I done something wrong here? Just a second. Well, yes, it is late, but I am an idiot too, so I forgot the square root. I'll do this. I was saying, wait a second, what's going on here? So what this equals is this equals the square root of mu divided by epsilon, right? And that's really mu sub 0 times mu sub r. We know mu sub r is 1. And that epsilon 0 divided by epsilon sub r. So that's what we've got there. And then that square root, and I should probably put some type of parentheses around here, because that square root of that, and you know that, right? Everybody knows that is this. Eta is the square root of mu over epsilon, right? Which is exactly the same thing I'm saying here. So that's the square root, and I did use the square root radical sign there. And now what I've got is I've got W over H plus 2 squared in the denominator here, right? Does everyone see that? I've got W over H plus 2 and then W over H plus 2, but I'm taking it to the square root. So what that leaves me with is 1 over W over H plus 2. Okay? Now, if I actually work this out here, mu sub r equals 1. Mu sub o over epsilon sub o taken to the square root equals 377 ohms. And then I've got epsilon sub r here too, don't I? So let's just throw that all together. So I've got 377 ohms. That's mu sub o divided by epsilon sub o taken to the square root. And then mu sub r equals 1, so I could just put a 1 here. You know, square root of 1 is still 1, but I'm not going to. And then I'm going to take that square root of epsilon sub r and put it in the denominator here. So square root, well, yeah, I guess square root of epsilon sub r times W over H plus 2, right? So that's what I've got. And when you look at that equation right there, that equation right there is exactly the same as this equation here. The only difference is 120 times pi instead of 377. That's the only difference that they've got. Epsilon sub r, excuse me, forgot the r, epsilon sub r down in the bottom, and then W over H plus 2, and I've mentioned where that 2 comes from, and that has to do with the fringing effects on both of those. Now I could have left that out, but it's too realistic to not put that in. Even though I'm not going to use this highfalutin equation up here that you're going to actually be using when you get out there in the field and you're working, you know, using these equations here, I just wanted to show you where that came from. So anyway, so that's Z0. And the next question is, what type of frequency are we going to be blasting across here? Well, let's say that our frequency is going to be 1 megahertz. I'm going to actually look at it with 1 megahertz, and I'm also going to look at it with 10 gigahertz. Now, I want you to remember that lossless line approximation, right? R prime equals 0, G prime equals 0 for both of those two. And that was the approximation that I made. Now, what we want to see is that a valid approximation? Is the attenuation so great that my approximation really is not correct? And so that's what I want to look at first. So I've got F equals 1 megahertz. I'm going to look at this right here. And we know that epsilon sub r is 4.5, right? We want to find out what the ratio of W over H is going to be. And so if I do a little algebra here, I think everybody can see Z0. Now I'm going to say that for this example, and this is standard, Z0 for microstrip transmission lines are usually around 50 ohms, right? Usually around 50 ohms. So if I wanted to find W over H, first of all, I've got the Z sub 0 over here, so let's take that and divide it by this, 377. So W over H is going to be equal to, the first thing we want to do is we want to take the 377 and we want to take that, so that over that, and then we can bring this up into the other side too, epsilon, square root of epsilon sub r. So I have 50 ohms, that's Z sub 0. Excuse me, divided by the square root of 4.5, that's epsilon sub r's, come up into Z sub 0. 377 goes into the denominator. And then we've got this in the bottom. So I put that up. Oh, okay. Well, I'm going to do it again, but I'm going to actually write it out this time. So W over H. The thing was, I did it on my sheet of paper there, and I did it in one. I wanted to do it in several steps. I did it all in one step, and then I tried to do it for you guys in several steps, and I screwed up. So I'm just going to write it down, what it is, and you guys can figure out the algebra in just a second. So 377 ohms, yes, let's put that in the numerator, not in the denominator, and then 50 ohms times the square root of 4.5. I'm not going to put a -1 there. That would just screw everybody up, wouldn't it? And then that whole quotient -2, right? Because we've got the W over H -2. So the actual ratio then is going to be 1.554. So if we say that the height, the thickness, I shouldn't even really say the thickness, because that makes you think of the thickness of the coating, and that's what this is, the thickness of. I forgot to say that this is not the thickness of the board. This is the thickness of the copper, right? The thickness of the copper up here, the copper coating. So even that comes into play, figuring out the exact characteristic impedance of that microstrip transmission line. All right. Now that's 1.554 ratio. So if I say that the height is going to be 2 millimeters, right? Because that's a standard thickness for a board, a printed circuit board. So the height's 2 millimeters. That would make the width of the line equal to 3.1 millimeters. Does everyone see that? So 3.1 millimeters would be the width, and then 2 millimeters high. I sort of made it a little bit thicker probably than I could have, but anyway, that's fine. And we used this knowledge of the characteristic impedance here, and the fact that we used the lossless approximation, and we figured out exactly what these ratios would be to get that 50 ohm impedance, right? Now, we've got all those. Let's figure out what R sub s and R prime is. R sub s is just going to be the square root, and I've written this out before, and I'll write it out again, times rho times pi times the frequency times the permeability of the conductor, right? And so when you do that and you multiply it all out, of course the resistivity of copper, let's just write that down someplace. The resistivity of copper is equal to 16 ohm nanometers, or 16 times 10 to the minus 9 ohm meters, which is what you want to put in there. And then F is just going to be 1 megahertz, 4 pi times 10 to the minus 7. Why don't I, I've got the number right here, 251 times 10 to the minus 6 ohms. But I just want to punch that in. So 16 times 10 to the minus 9 times pi times 1 megahertz times 12.56 to the 10 times 10 to the minus 7 equals, taken to the square root, and I get that number, yes, 2.5 times 10 to the 4, or as I wrote it down, 251.3 times 10 to the minus 6 ohms, 6 ohms. All right, so that's R sub s. R prime, as I've written up here, is just going to be 2 times R sub s divided by W, and of course W is 0.0031 meters. Always remember that we're talking in terms of meters, right? So everything has to be brought back to its primary units so that we can use it with things like R sub s, which are ohms, which are a combination of primary units we know, right? So if I multiply that and divide it by 0.0031, what I get for R is 162.1 times 10 to the minus 3 ohms per meter. So now we've got all of the things that we need to figure out what the propagation constant is going to be, right? We have figured out R prime. We figured out C, no, we haven't figured out C prime, have we yet? We've got the equations, but we haven't actually figured out C prime. Anyway, we got R sub S and we got R prime. C prime should be no problem. C prime is going to be, well, we've got the equation here, so it's W over H, and we know that's 1.55 plus 2, so that's 3.55. 3.55 times 4.55 is going to give me 15, and 15 times 8.85 times 10 to the minus 12 is going to give me something that's larger than times 10 to the minus 12, isn't it? That's right. And so that's what I get with C prime. I get C prime is 141. I will let you do the math here, right? I just did it sort of in my head for you. Remember, epsilon sub 0 is 8.85 times 10 to the minus 12 farads per meter. So when you put that all together, you get 141 picofarads per meter. And for L prime, I'll let you look at the L prime thing, mu, of course, mu sub r. Let's not forget when you're doing this that, you've got to remember that you've got epsilon sub r here, and that equals 4.5, and we got to put that in. Not so for this one, right? Because you really are always just using epsilon sub 0, because epsilon sub r is always 1 in anything we're going to do. Or did I say epsilon? I meant mu sub r is always going to be 1. So L prime, when we put that together, 1 divided by W over H, so 3.55 is what it is. So this divided by, so 12.56 divided by 3.5 is going to be something like 3.5, 3.75, something like that. So what we end up getting for L prime is 353 nanohenries per meter. And I'm going to finish this up in our next lecture by looking at what the propagation constant would be and why I can say a lossless approximation is not a problem. In fact, I want to point that out to you. That's one thing that I want to look at in our next thing. And why isn't it a problem? Why would R, think about this, R prime, why, let's cut this out over here. Why would R prime equal 0 ohms per meter? Why would that happen? A very short length, right? Very short length. So let's say that I'm only going 3 meters. I don't care what R prime is. I don't care what R prime is because I'm only going 3 meters. It's almost, it really doesn't even matter almost, right? So I get something that's 20 decibels per meter. I'm only going 1 meter. So short length is a reason that we can assume that R prime is going to be equal to 0, right? We can neglect that. What's the other reason? Low frequency. Low frequency or short length, we can make lossless approximation. And that's what I made here. That's why I made this lossless approximation here. What we're going to see working with these and coming up with the propagation constant now is that it doesn't matter. It doesn't matter. You're only going across your phone. You're only going across a computer's motherboard. So it doesn't matter. And you'll see that. Okay, I'm going to hold that. That'll be my last lecture for today. Those horrible SpaceX guys didn't go to space. But you want to sort of put that off. They did have one that that blew up, right? And that was that I think Israeli satellite one, or some satellite by somebody. Anyway, Okay, let's head on to the next lecture.